coworker here, Michael Epley. So just by a show of hands, who here has not heard of Red Hat? All right, that's good. That's good. So one of the things that we like to say is that we are a software company with an open source development model, right? We believe that developing software the open source way is the best way to develop software. And so one of the things we're very widely known for is a distribution of Linux called Red Hat Enterprise Linux. And what we're seeing in the community is that Linux is pretty much everywhere, right? From high frequency trading systems that power financial systems to high performance computers, the fastest in the world. And so for a number of years, we've been focused on expanding our footprint into edge computing and automotive. And part of the reason why we wanted to come here and present on some of the things we're working on is because we see in the space community this growing interest in having access to more powerful computing, things like NVIDIA Jetsons. And so I'm here to tell you that, Red Hat Enterprise Linux is actually supported to run on the entire Orin line of NVIDIA Jetsons. So hopefully some of these open source projects that we've been working on, you'll find relevant. And what we're going to do is I'm going to turn the slides over to my colleague here, and then I'll be back to demonstrate some of the things that he's going to talk about. So thank you.
How do I click slides? All right. Yeah, thanks, and appreciate the introduction, Tony. And one of the things that we highlighted on that title slide is bring that open source innovation. As Tony kind of alluded to, the goal for Red Hat is to look across the entire industry and lots of different use cases and lots of different industries and take all that innovation and bring it back into the open source community. And for us and for the flight software community, the goal there is to understand your domain. And we've been watching these talks the last couple of days and really focusing in on what are the kind of challenges that you're facing? Things like the new and emerging hardware, AI accelerators or GPUs, the use of, say, real-time mode and things of that nature. And understanding what those challenges are, whether it's kind of supporting your mission. We also heard a lot about updating your software and updating your systems while in operation. So updating those software over that lifespan and keep in mind, long mission lifespans, what we're talking about here, while we support, say, the operating system, in some cases, 15 or more years, even for a short lifespan in the context of, say, a year or two for a LEO mission and a large constellation, maybe a cybersecurity threat might mean that that update cadence has to keep pace with the needs of that cybersecurity threat. Patches and updates that are relevant for that might happen in days or hours. We're also seeing, as kind of Tony alluded to, this complexity, an increase in complexity of the types of hardware systems, distributed systems of these flight computers and of these larger scale constellations now that matter, and increasing that software complexity. If you're talking about, say, managing a large constellation where you've got a lot of variability in terms of, say, the age or the generation of that hardware and that software, managing that complexity now becomes a big risk. And the individual platforms themselves are also now increasingly multi-core, using different accelerators, lots of different software modules as part of that. And then I mentioned cybersecurity as well. And I've heard several people mention it kind of in passing the last couple of days. Cybersecurity as now a driving force into their system design and system architecture. And so how do we tackle cybersecurity concerns in these types of systems? And again, as these systems grow, and I'll use the constellation example, and somebody talked about enabling telco RANs, for example, in our LEO constellations. Right now, you're opening that platform up to essentially untrusted networks, traffic, and untrusted workloads potentially running on those platforms. And those sorts of things mean that we have to pay attention a lot more to security. The compliance of things like your telco standardization are now going to start impacting your flight systems. And this is why we want to bring that innovation to open source, because Linux is the community which we can take all this in, attach it to, and build capability already on that platform that's been used for now 30 or 40 years. And we've got a huge diversity of those use cases, a huge test and validation community from real world users of that platform and that operating system, backed by things like Red Hat, that we can do the security and compliance controls for you, build those attestations, support more and more diverse hardware boards, and other components within that operating system. And I mentioned real time earlier, and that's something that, for example, the Linux community has been building into the Linux kernel for over 20 years. And now it's finally mainlined and part of the default Linux kernel package. That means it's not a new thing. This is now a tested and robust subsystem inside of Linux. In fact, just yesterday, I heard from somebody that they turned on real-time mode and absolutely nothing happened. And that's exactly what we want, right? No changes, right? But of course, if you've been paying attention in the Linux community and in the enterprise space over the last, say, 10 or 15 years, the new cool hotness is container technology. This is how the world is now building and developing your application software. And containers are awesome in lots of ways, and I could wax poetic about that for a long time. Probably first and foremost is they provide a lot of just direct measurable benefits. They're designed to be immutable right out of the box. When you make a change to a container, you don't just go and change that software image directly. You rebuild it from scratch, essentially. And they're also inherently designed to be modular and portable. The container image itself is fully encapsulated and self-describing with a bunch of metadata. And all that means is that you can now separate these concerns of building that application and that software and that workload from the underlying platform that's going to execute that too. Now, we've been doing this for applications for a long time. What we really want to talk to you today is, well, we can take that same pattern, take all the benefits that these application developers have been enjoying and accelerating technology in the IT and enterprise IT space, now apply that in other places by taking that same concept and applying that to other parts of our systems. And today we're focusing on that idea of applying that to our operating system. So can we do this for operating systems? Absolutely. So we're going to talk about how we do that now. And for Linux, it's called image mode. And this is the idea that we're going to take a container and we're going to create essentially an operating system image using these container technologies as individual layers that we can stack on top of each other and then build a bootable operating system image from that. The whole idea here is it's proven technology. We can now leverage all the capabilities that we have for building these applications, all the CI/CD tools, all the test tools that rely on container technology, those characteristics of the technology itself, things like the immutability, to make and improve the confidence of our build process. And all that means, especially things like CI/CD and all the automation that we can bring to bear to there, means that we can move faster, we can rebuild and retest and revalidate our software much faster with far less risk as well. All right, so what does that container workflow look like? The nice thing is it's actually very simple. Container technology is designed to be declarative. You define what that image and what that container should look like, and automation takes over from there. If you've ever used container technology too, it's kind of designed and separated into three things. You've got a CLI, and here you see our version of that CLI. If you're familiar with Docker, Docker equals Podman. So Podman is our version of that CLI. It takes that declarative metadata, the container file itself, and then creates an image. And then when you deploy that image on that far right side here, a container runtime interprets that declarative statement and that metadata inside that container image, unpacks it into that running application in your system. And this is how container technology works from an application perspective. It works the exact same for an operating system. You define your operating system, the automation takes over for building that operating system and that image, and then you deploy that just like you would any other operating system image. And that works for VMs, bare metal, or anything else. So no matter where your deployment target is, the advantage of the system is the build process, your CI/CD, everything looks the same no matter what your deployment target is. Your test and validation environments, your bench tests, your actual flight test software, your production deployment, the idea is everything looks the same. So no matter what, you get consistency. And when you deploy into your test environment, and you can have confidence that that same deployment will work the exact same way using a production deployment and using the production deployment target. Similarly, all the tools that we use for that are going to be the same tools. You don't need a separate kind of build process. You don't need a separate deployment process. You don't need a separate content distribution process for these different parts. All right, last part, and what I get really passionate about is the security and compliance aspects of that. just like we can automate the build process, we can automate security, the validation, the attestation, the generation of tests and evidence that we've executed those tests during that process by applying that same automation. So do things like software composition analysis, vulnerability analysis. We can do our static and dynamic testing. We can deploy, because we're using this automated deployment, into any environment we want to run those tests. And then finally, instrument up our packages using automation for things like observability, logging, telemetry, or any other aspect that we want, and make that, again, process very repeatable. So for enforcing security updates, for example, the fact that we can repeat that means that we can apply these updates with confidence without having to worry about breaking something. All right, that's the end of my spiel. I wanted to get through that quickly because really we wanted to get into a demo and show you how all this stuff works in the context of an operating system. I'm going to turn the floor over to my colleague, Tony.
All right. Thank you, Mr. Epley. So I assume most of you have touched containers, seen a container file. So if I were to pull one up, it should look relatively familiar. So here is an example container file that we're using here. This particular one is, if you've ever heard of an open source flight simulator called Flight Gear, this is a particular container image right here that embeds Flight Gear with the Red Hat Enterprise Linux bootable container base image. And so I'm going to demonstrate here that we have this kind of kiosk mode set up where the system automatically boots into the flight simulator, and then I can, on the fly, essentially change the personality of that system and reboot into something else, right? So it kind of creates this idea of like a software-defined system that, based on whatever container I have deployed, that's what the system is. And that, I think, becomes more interesting to space systems, because let's say, you know, you need to push out an update to really change what a particular spacecraft is doing, or maybe what a satellite is focused on due to, to respond to like a national disaster or something like that. Using this kind of technology, you can do that. And oh, by the way, it also works for just standard updates too, right? So I've got two particular demos I'm going to show. One is this kiosk type approach, and the other is showing a full operating system upgrade using this containerized workflow. So I have two systems here. Wouldn't be a demo without some command line stuff. Okay, so all things considered, this is just a standard Red Hat Enterprise Linux 9.4 system. If I pull up the console to this system, it booted up, and it is currently operating in using the GNOME desktop, using the kiosk mode stuff that's isolated with SE Linux to, you know, make it, it's really purpose built for things like point of sale systems, or an environment where you have a system that you need an application to run and multiple public users are going to have access to it and things like that, right? Right now, it just booted up into a Firefox web browser. And to save time, I've already pre-staged the container image on this node. And the open source project that we're using behind bootable containers is creatively called bootc. It stands for bootable containers. And so if I run a bootc status, we'll see I have this rollback image here called kiosk F22. So in case you were wondering, the F22 is going to be the F22 airplane model from Flight Gear. So what I'm going to do is a bootc rollback to automatically make that the live image for the next boot. And so in a production instance where I'm trying to, you know, upgrade my system, we have like the bootc upgrade command, bootc switch, if we want to just totally switch and rebase onto a new container image. Just to save time, I just did the rollback so that we can not have to sit here waiting for things to apply and all that kind of stuff. So once I reboot the system, you'll see in the background, this particular virtual machine is rebooting. And as soon as it loads up, instead of a Firefox web browser showing redhat.com, we're going to see the Flight Gear flight simulator starting to load, right? Now, this is a virtual machine, so unfortunately, if it actually gets to the point where it's loading the airplane, you're going to see it like jittering and just terrible performance. So as soon as we see the Flight Gear screen start to load, I'll switch to the actual RHEL system, and then I'll take a poll and, you know, kind of let you guys determine how I should upgrade RHEL, because I have a couple different options I can show you. Stand by. I was hoping all that talking would have got past the initial boot, you know. So while it is booting, one thing I did want to point out is uh, there was two conversations ago or two presentations ago, there was mention of data centers in space. Um, we think it's an interesting use case, right? Data centers in space are probably not going to be exactly the same as data centers here terrestrially. But a couple of weeks ago, we made an announcement with Axiom Space that we're collaborating to support their plans to build data centers in space. So we're kind of interested in it as well. But here we go. There's flight gear. We'll go ahead and close that because that's not going to be a pretty sight. But for the audience participation demo, so this particular one is just a REL system. I believe it's 9.4 is what I'm running. So currently booted is 9.5, so I can roll back to 9.4 if I wanted to. But we have a couple different options. So I've staged the container images here locally to simulate kind of disconnected updates and things like that. And we have a couple different options, right? I can totally rebase this thing from RHEL to Fedora, or I can do a major version upgrade and go from RHEL 9 to RHEL 10 beta. So show of hands, who wants to see RHEL to Fedora? Okay. We can't do Ubuntu. Sorry. I don't know if I would still have a job if I demonstrated that. Okay, show of hands, RHEL 9 to RHEL 10. Okay, I think RHEL 10 gets it. Now I just got to remember the command. So it'll be a boot C switch transport equals directory because I have this thing stored here in the directory. And then I believe it's, oh, can't type. And RHEL 10.0 beta. Let's see what happens. All right. Got the command right the first time. Now this will probably take, I don't know, a minute or two. What it's doing for those, it sounds like everybody's familiar with containers, right? So because we're doing a major operating system upgrade, there's a lot of changes between the different image layers. So when you're doing this, the benefit of having the container image kind of staged locally instead of trying to pull over the network for space systems, I think it's pretty apparent, right? You don't have to wait for network outages or slow bandwidth, all those kinds of things. So as long as you can get the image data up there, we can reliably apply that upgrade to the system. And then we have some additional things that I'm not going to demonstrate here, but would love to talk to you about later on today or tomorrow throughout the week. But we have technology, an open source technology called Green Boot that we can use that does health checks. So one question I'm sure somebody's probably wondering is, okay, I applied a major version upgrade to my system and my applications now that are running on top are broken. Like, how do I fix that, right? Well, with Green Boot, what we can do is define health checks that actually can happen and check things before the operating system is fully booted. And so when you attempt to boot, if Green Boot, any of those health checks that you define fail, it will automatically roll back so that you can ensure resilience of the upgrade process. And so it looks like that bootc switch finished. And right, just to confirm, I am running a RHEL 9.5 kernel. So let's wait for this guy to reboot. It's right here. I did hit enter, right? Yep. Here's that pesky grub thing again. And I think after we're probably close on time. So after this fully boots, we can probably take a few questions and we'll be hanging out the entire week. So happy to engage in further dialogue, but I think it should be up. So if I do a uname R, right, we see it's a RHEL 10 kernel. Of course, this is beta, and of course, cat OS release. And we see RHEL 10, right? So a live upgrade from RHEL 9 to RHEL 10. And then when you think about, what that means, Red Hat Enterprise Linux is known for having an extremely long life cycle, which kind of aligns with these mission critical space systems life cycles. So by default, a major version of RHEL is supported for 10 years with the option to go to 13 years. We can extend that with this so that the system's essentially unlimited support lifecycle from a Red Hat standpoint, right? But yeah, was there something you wanted to? Yeah, so feel free to take a look at the slide deck. We do have a number of other slides that we didn't cover. One that I'll show here just real quick is we do have a starter kind of Bootsy image that I was demonstrating here. This was a question I got asked in a conversation last week, like, what's the size of the image? What does it contain? You know, all those kinds of things. But I'm sure all of you know there is a relationship between Red Hat Enterprise Linux and Fedora and CentOS, right? So Fedora is kind of like the bleeding edge where all kinds of new innovation and things are tried out. So there is a Fedora Bootsy image as well. And then CentOS, which is essentially the upstream where things go from Fedora before they end up in RHEL. There is also a CentOS Bootsy image as well, if you wanted to check that out. And there was a conversation that happened before our presentation as well. Someone was like, you know, I use CentOS because, you know, I have to pay for RHEL for development and all those kinds of things. But one of the things that's not widely known is that RHEL is actually no cost for non-production usage. So, you know, we do encourage you to test on RHEL because, you know, it's beneficial to test in what you're running in production. So any questions?
No, I do. Thank you so much.
Nice.
Just 1 second. We're
Raise your hand
waiting
again.
for a couple of questions. Somebody is typing on Slack and I'm still waiting to come through.
Can I drop from the Zoom?
Okay, so when I was like
Just
looking
kidding.
at the slides, I saw like OS tree. How does this relate to Fedora Silverblue? Because that was something I've seen OS tree exist in before. Is this
Yeah.
like some extension of what Fedora Silverblue was?
Yes, so OS tree is still one of the technologies that's used in this. So if you've been following Fedora, right, there's Fedora Silverblue, there's Fedora IoT, right? Yes, to answer your question, yes, OS tree is included in this with an extra layer to embed the kernel within the container so that we can create like a fully bootable thing.
I actually have a question. So I think one of the things in this room that we have used RHEL for in the past is real-time testbeds. I think that's a very consistent use. With the preempt-RT patch getting into Linux mainstream, is that available? When will that be available in RHEL from your perspective?
Yes, so we've been shipping the real-time patch in RHEL for years, right? So one of the value adds that Red Hat provides and why we're able to support a version of Red Hat Enterprise Linux for 10 years plus is our policy for backporting, right? So we do not plan to ship in RHEL the latest and greatest components. If there's something that our customer and partner community is looking for, depending on the life cycle that like a version of RHEL is in, you know, we'll pull in pieces that are newer and maintain those for, you know, some period of time, things like that. But the preempt RT patch has been shipping in RHEL since like RHEL 7-ish. Yeah. So with that said, when RHEL 10 ships, I believe, I forget what the kernel was that was just on this demo I was showing, but if it's 6.12 or newer, it'll have it built in instead of you having to enable it, right?
I'll take one last one from online. How does RHEL handle custom kernels or kernel patches commonly required for embedded systems?
It's a great question. You want to answer that one?
I'll give you the first credit.
Yeah, so historically, we have not supported custom kernels, right? Because one of the things that we like to do or like to say is, you know, RHEL runs in a lot of different mission critical environments. And the reason we are able to support those environments is because we know exactly what has been delivered and what's running across those various environments. With that said, myself and my colleague here, we actually work out of Red Hat CTO office, and part of our charter is to figure out what kinds of things Red Hat needs to do to evolve to kind of expand our reach into various communities. And so, as I mentioned earlier, we're already focusing on edge computing and automotive as kind of broad industries. With that said, from an edge computing standpoint, where we focused so far has been like, I don't know, putting an Intel NUC in a closet somewhere remote, right? And, you know, I think there's room for improvement there. And I think to answer the question more directly, we are already working on things like functional safety for RHEL, and looking at these various small single board computers that exist in the automotive space. And some of our efforts there are kind of forcing us to relook or reconsider how we deliver the kernel and how we support our partners extending the kernel to meet their needs. So not a direct answer to say like, yes, we support it today, but it is something that is being looked at, and would love to talk to anyone who has a particular board in mind that they're looking at. I will say that we are actively talking to Microchip about the HPSC. So that is a thing. Fedora already supports RISC-V, and so that's a step towards things getting supported in RHEL. It has to be in Fedora first. So yeah, it's a answer, but a non-answer, sorry.
Great talk. Thank you so much.